Okay. Guys, today we're going to start working on what's known as bisectors of triangles. Okay, we're going to look at two specifically today. Okay, Michael, can I get my essential question for me today? What are we trying to answer here?
What conjectures can you make about the perpendicular bisectors and angle bisectors of a triangle?
We talked in the last section a lot about angle bisectors, and we talked about perpendicular bisectors. Okay, perpendicular bisectors as they relate to segments, and we talked about angle bisectors as they relate to certain sides of an angle. Okay, there was a word that we used last section. Don't want you to forget it. We need to look at things that are equidistant when we talk about perpendicular.
That's a funny word.
Yeah, it is.
It looks like someone made it up. They put the words together.
Yeah. I like that word, equidistant. Maybe I should get a fish and name it that. That'd be cool. Okay, but I already have a fish named Ferocious.
Do you really?
Oh, yeah.
Ferocious.
Kind of mean. No, it's not a piranha. I don't believe in just watching other fish get mutilated by a piranha. Okay. All right, here we go. Guys, our goals for today then is this. There's going to be two things that relate to perpendicular bisectors and angle bisectors, and they're going to relate to triangles in the fact that they're going to help us find the circumcenter of a triangle. I'll tell you what that is. And find an incenter of a triangle, and I'll explain to you what that stuff does here in a little bit, okay? But in order to be able to be successful today, we definitely have to know the vocabulary here. We want to know the vocabulary. So, first one up there, concurrent. Concurrent says when three or what? More. I don't care if it's a line, I don't care if it's a ray, if it's a line segment, intersect at what?
Point.
Same point. So an example, you got to have at least how many kids?
Three.
Got to have at least three. So maybe here's one. Here's two. Here's my third one. Maybe even a fourth one. The idea is that all of those lines do what, kids?
Meet in one place.
They all meet in one place. Yep. These lines are considered concurrent because they all meet at that one point right there. Okay? So concurrent because they all meet at that point. So if I say lines are concurrent within this diagram, we say they're concurrent because... Yep. Okay. So when we talk about points of concurrency, kids, it's going to be the point of intersection of the lines, rays, or segments. That's called the point of concurrency. Okay, so these lines are concurrent lines, and this point, the point of concurrency is right there. Okay? The lines are concurrent because they all meet in a point, and that one point is called the what? Point of concurrency. Okay, so that's easy enough, isn't it, kids? Some big words. Okay, next one here, kids, called the circumcenter. In a triangle, the three. What's the phrase after three? Two words after three.
Perpendicular bisectors.
Perpendicular bisectors are concurrent. That point where the perpendicular bisectors meet is called the what?
Concurrent.
Circumcenter, okay? So circumcenter is based off of, I'm just going to write this down here. It's based off of perpendicular. Perpendicular meaning how many degrees? It's based on the perpendicular bisectors. Okay? Then the incenter. Just as a triangle has three perpendicular bisectors, it also has three angle bisectors. Not a segment bisector, but an angle bisector. The angle bisectors of a triangle are also what? Okay. This point of the concurrency is called the incenter. So angle bisectors form your incenter. So the angle bisectors are going to form an incenter that we call it. And then we'll look at some examples and show you how this relates. But terminology-wise, this. Here's how I remember this. Okay? People are like, does perpendicular bisector or angle bisector make the incenter or the circumcenter? Here's how I remember this. Angle bisector. Angle starts with a vowel or a consonant.
Oh.
Inner starts with a vowel. Okay? C and P. Okay, that's how I kind of remember it. Okay, angle bisector, incenter. Just think vowels for that, okay? English department would be proud of me today, wouldn't they? And then perpendicular bisector. We need to remember this. Perpendicular bisector bisects a segment, so just a visual quick again. If this is my segment right here, and I have a perpendicular bisector, what's true about the angle formed? 90 degrees. And what's true about this left segment up to the perpendicular bisector and the right segment beyond the perpendicular bisector? So I should put some tick marks here and here. If I picked any point on the perpendicular bicenter, we would say that point on the perpendicular bicenter is blank from the endpoints of the segment. Equidistant is the word, okay? And then you guys know that an angle bisector takes an angle right here and cuts it in what? Half. And any point here is what we say equidistant from the sides, as long as we are measuring the distance in what form of an angle?
Perpendicular.
Perpendicular. Okay, so we know that. We've talked about that. We've done that. We should know how to do that part. Okay? What do angle bisectors of a triangle form according to our vocab first?
All.
Equal angle bisector.
It's called an angle bisector.
Well,
What's an angle bisector forming in a triangle?
I don't know what side.
The incenter. And we're going to say the perpendicular bisectors form the...
Circumcenter.
We'll show you what this means here, okay? I like this stuff. Here we go.
I have this got really intense.
We kind of looked at this example right here already, but to warm up.
Warm up.
2 laps, Audrey Klein, go.
Okay, sorry.
3 because you made fun of that. Okay? All right. We already talked about this, kids. Where in the world, and again, I'm going to tell you right here, kids, I'm going to tell you right here that first of all, what looks to be true about these, are we bisecting an angle here or what?
Yeah.
We are, okay? So we kind of say, well, these are all going to meet. What's this point called again, kids?
Circumcenter.
Okay, what do you notice about these line segments? Well, they meet in the what? They meet in the same point, don't they? Or meet at the same point? They meet at the same point. By the way, this one's kind of a tricky one. This is actually a circumcenter and an incenter. Okay?
Because the circle's inside it.
It is. It certainly is. Okay?
No doubt.
And the reason it is because it's both an angle bisector and it's also a perpendicular bisector of both sides. These angles right here, 90 degrees. So we'll talk about this as we look at stuff today, okay? But again, the thing that I want you to point out is this. When we're doing stuff, I don't care if it's an angle bisector or perpendicular bisectors, you're going to have points of concurrency in here. And we'll talk about the difference between what a circumcenter is and what an incenter is when we form those, okay? First, let's start here. Solving a real life problem. Let me blow this up a little bit. Does that print off? Can you read that okay on your paper?
Yeah.
Okay, so pretty good.
See if this is real
Okay,
life.
getting some of these on here is kind of tough. So let's talk real quickly, kids. So I have an example right here.
I don't think this is a real life problem.
Oh, I think it is. It says a powerful operator wants to locate a what, kids? So that it is the same
Distance.
from carousel C. Okay, so the carousel C is here. The Ferris wheel F and the bumper cars B. So we've got this triangle BCF right here. Carousel's up here. Bumper cars are here. Ferris wheel's here. Okay?
It's gotta be in the very middle.
Find the location of the food stand S. Okay?
Is that always possible?
I don't know.
Because think if the Ferris wheel, like, just pretend it's like further down to the right.
Maybe.
Like, then it couldn't be the same distance, could? Or maybe it could. You have to
Maybe
get
it
to the right more.
I made a theory. This is not real life.
Why is this not real
Because the
life?
Carney guys is not going to take that much math to find that. And have you seen the Carney guys?
They don't even have
They don't
teeth.
even. Yeah, they can't even do math. They smell like crazy.
Now, listen.
Unless related.
Let's not be stereotypical here, all right?
I don't know. Have you seen the Carney guys?
Well, yeah, but you know what? I bet some of those guys are pretty rich too.
Yeah.
Yeah, because it's screw up.
Yeah.
If I'd have known this conversation was headed here, I would have never picked this example. Okay? All right, here we go, kids. The deal is this. just kind of talk about where you think you would want to locate your stand. If you knew that you knew the carousel horse was there, the bumper cars were there, Ferris wheel was there, you think that there's probably going to be people. Where are they going to want to locate a food stand? Just give me an idea.
I just put it right in the middle.
Probably not next to the bumper cars. 'cause
Somewhere in the what,
Go
though?
right next to the carousel.
Right, because you want
Why did
people.
tornadoes like throw up?
Like you can eat food on the Ferris wheel.
Oh,
but
my
you can't really
Lord.
eat food in the bumper cars.
Yeah, but everyone wants cotton candy right after they get off the carousel.
Yeah, that's true.
Yeah,
Well,
because the little kids are always like, Mommy, Mommy.
they want so it's the same distance from the carousel, the Ferris wheel, and what else?
The bumper car.
Bumper cars, okay? So here's how this works.
You do a 90-degree angle.
You could. So what it turns out to be is this. When you have a triangle right here, the point that you're looking for is called the circumcenter, okay? The circumcenter basically is going to be the same distance from there out to the points there. So circumcenter is going to look like this here. I'll show you what's going to go on here. We're going to look at perpendicular bisectors here for a second, and I'm going to draw it as best I can up here. Does that make sense to everybody? Okay. You'll want to kind of sketch this in here, but I'm going to show you kind of what's going on here, all right?
So we're doing
So-
perpendicular.
Yep. And we're going to make it so it's 90 degrees as best as possible. So you may or may not want a ruler for this. I can hand these around here. Don't mess with the pens that are in there. Just grab a ruler if you need it, okay? Here's how this would work, kids. Has anybody seen my... there it is. Okay. Okay, here's what we want to know about circumcenters, okay? I'm going to tell you right here, this is a circumcenter problem, all right?
What are those? What kind of pen is that?
Okay. Me and Adam are gonna draw the carny guys. We got you covered.
Okay, I'm going to measure this right here. I go from 21 to 36, so how long is that side?
21 to 36. 21 minus 36 would be 11. 15. 5. Dang it. Oh my gosh. I'll figure it out. 21 to 36. Okay, so we got, if you would add 10, it would be 31 plus 5, so 15.
So 15, right? So this distance down here is 15 units up here for me. So for me, what's half of 15?
7.5.
Okay, so I'm going to find the middle here. Okay, my middle's right about here.
Oh, it has to be the middle.
My middle's right about here.
But it won't be a 90-degree angle if it's the middle.
Okay, so what I'm going to do, everybody listen. Everybody listen. You guys listening? You guys not distracted?
No.
Okay, pay attention. All right, I'm going to draw my 90-degree angle as best I can here. Now, is that 90-degree angle going to go through the opposite vertex or not? No, and that's okay. I'm going to kind of put this down here like so, and I'm just going to draw a line that goes right about from here to there on that side. So, looks like to me, here's one perpendicular bisector. Okay, from here to about there. Does that look like about a 90-degree angle to you guys?
Pretty close.
Let's get the protractor out of the way.
Oh, you want
I
that
could.
to be a 90-degree.
I'm going to guess I'm pretty darn close. Is that okay?
Yeah.
Okay, now watch this right here, kids. I'm going to do a perpendicular bisector for another side. Okay? How many points do I have to have?
3 or more.
No, this is the question. I screwed that up. How many lines would you have to have before you could find a point?
Well, 2
Well, 2.
Technically 2, but we could test that third one to see if there are going to be points of concurrency when I do that, okay? So let's do the perpendicular bisector from the carousel to the bumper cars. I'm going to measure this out. This measures out to be, well, up here on the board anyway, I'm getting at 11 there, so what's half of 11? 5.5, would you guys agree with that? So find your middle. I don't know, you might have to measure it. Mine is right kind of here at 5.5. I need to measure that again. 19 points, so right about here. There's the middle of that. And then I want to go ahead and go perpendicular to that. Would you guys agree? So that's going to go right about there. So if I draw my line, kids, if I draw my line from here to here, oh, I didn't want to do that. What happened?
Yeah, we used to have them. It'd be like not really.
From here to here. That's perpendicular bisector right there.
Wait, what's the second dot?
What, just these two?
No, what's the?
That dot right there is not even supposed to be there.
Oh.
Okay?
Okay, it's okay.
Here, let me try to do this.
Mine doesn't look anything like yours.
Well, dab nabbits.
What are you doing? Boy.
What are those things?
Your business.
Markers?
Okay, now guys, if I do a perpendicular bisector of the third side from C to F right here, because my 90-degree angle is sitting right here, right, kids? Don't have a 90-degree angle here and a 90-degree angle right there. If I do a 90-degree angle perpendicular bisector over here, where do you think it's going to hit? Let's just see how close we are. Let's see if I measured correctly. Looks like C to F is,
CF?
what's half of 12 and a half? 6 1/4? So 23 is 6. A quarter is about here. So it looks like right about there is my midpoint. On that side, if I go perpendicular, does it look like it's going to hit right down there if I go perpendicular to that side?
No.
Yeah, I think so. Pretty dang close. Okay? Pretty dang close. So I'll do this. What do you think, guys? Did it hit that point right there? Okay, so here's the deal, kids. Listen carefully. This point right here is on all three, what kind of bisectors again?
Here, let's go back. Circumcenter, Incenter.
Well, just listen to what I say. What kind of bisectors were we dealing with here? Perpendicular bisectors are going to be equidistant to all endpoints. So if I have this, the distance from here to here is going to be the same as the distance from here to here. Okay? This point right here, watch what I do. I'm going to do this in a different color. These are on perpendicular bisectors, right? Watch and listen carefully. We would like that food stand to be in a place where walking from my food stand to any of those three activities at the carnival would be the same distance. We want it to be equidistant from all 3 points. So watch what I do here. This is very important. Go purple with this. This is our circumcenter right here, right? Is it okay if I call it C? Okay, that point is on a perpendicular bisector. What's going to be true about the distance from this point to B and this point to F, kids? Okay, but listen to me. From here to here, these are going to be the same, right? But another perpendicular bisector, same point, going from this to C to F, well, the distance from here to here is on another perpendicular bisector, but still, it's equidistant from the... It's equidistant from the what?
That does not look right. That's a lot of mark.
That is not okay.
Now watch this.
Right? Do we need to measure it, guys? Because I'm...
He's the teacher. He's always right. Stay with the fact.
Oh!
That circumcenter is like the center of a triangle where these points are part of the... And what's true about a radius to all those points?
It's the same.
Okay? That triangle is like part of a circle. It's like finding the center of a circle. Okay? So that circumcenter is the point in the triangle where it says, get in that triangle, find a point. And if I say run to that vertice, run to that vertice, or run to that vertice, what would be true about those distances?
It doesn't matter. They're all the same.
They would all be the same. Okay? So here's the deal. Circum means go outside this. Okay? It means if you want to make a circle to circumscribe around this triangle, the circumcenter is the point you would need because the distance from C to F is the same as C. Actually, they have a C up here and B. And that's found by finding all the what? Perpendicular bisectors or angle bisectors? Okay, perpendicular bisectors find the what? And this is the center of the triangle. It says the distance from that point to each vertice is the Same. So the circumcenter, I'm just going to write this down. You should put that food stand right there. The circumcenter is the point. Whoops.
I feel like you wouldn't. Why wouldn't you put it on one of the ones?
What kind of food stand is this?
Mexican food, probably.
It's the point where
No, it's like fried butter and stuff, guys.
I
it.
had the fried butter on a stick.
Yeah, that was way good.
And I don't have diabetes.
That
so
tasted
we're
like a
okay.
cinnamon roll. Like I would eat 5 of those in one day.
I've never
Hey,
had one.
hey. Let's not be discriminating against Christmas dinner today, okay?
I don't know.
I'm gonna
I wasn't
discriminate because I'm a
discriminating.
wrestler.
Yeah, I don't.
Point where it is equidistant from.
Hey, Josh, it's like dying. How you holding up, Josh?
Write that down, please.
Very
The circumcenter is the point within a triangle such that that point is equidistant from all 3 vertices. Can you handle that?
Yeah. Not too shabby.
Okay.
That makes sense.
Circumcenter means go from a point to point, point to point. All right? Point to point. Vertices are points. Now, we're going to talk about a situation where we're not going to points anymore, but we're going to sides. Okay? And that's going to be found by looking at angle bisectors and how they relate to being equidistant to sides, not points. So let me show you what's going on here. Guys have example number 1 down? It is so cool. Okay, let's go to example 2 then. Example 2 says finding the what, kids?
Circumcenter.
Okay, let's see. Circumcenter. Is that angle bisectors or perpendicular bisectors?
Perpendicular.
So are we going to be bisecting sides or are we going to be bisecting angles here? Sides. Okay. All right. So our points. Let's get our points up here.
Okay, let's do it.
D is what point? So I'm going to go right 6 and how much? Up.
4.
That's D. E is where? Oh, gosh, dang it, I screwed this up. We'll have to estimate where D is. Left 2 and up how much?
4.
Really? You done did it to us?
And then, gosh dang it, this is a bad example. That's okay.
Let's just change the number.
Okay, yeah, let's do that. That's a great idea.
4, that was a bad number.
Let's do this. I can make this work. No, I can make this work.
Please, it's 6, 4.
Let's do this. Let's go, let's change all these points.
This just makes fun.
Let's do this. You ready?
7, 3, 6.
Come on, humor me and tell me you're ready.
Yeah.
Let's call this, okay, let's get rid of all these. Call a point D equal to 8, 6. E is going to be 0, 6. And F is going to be 0, 0. Let's do that. That'll fit in the first quadrant, won't it? So get rid of these points. That's a bad example. Way to go, Parson. Way to go, Parson. Okay. What are we trying to find?
Find the corners of the circumcenter.
Find the coordinates of the circumcenter. In other words, find that one point such that if I took off from that one point in the triangle and ran to a corner of the triangle, those distances on a straight line would be the same. Okay? Help me plot these. What's my first one, kids? 8,
6.
what's the next one?
0, 6.
What's the next one?
0, 0.
All right, draw your triangle in there. I'll do my best to draw it as well.
It's a right angle.
That's good news, isn't it?
I don't know, is it?
I don't know. I think it is.
Then the other two.
Okay, kids, is a circumcenter found by doing angle bisectors or perpendicular bisectors? What is it?
Angle bisectors.
Ah!
Well,
Perpendiculars,
it's
right?
the same because if you would bisect the angle, you would get into the middle.
Well, not necessarily.
Really?
Mm-mm. No.
Well,
If it was an isosceles triangle, you would, but not all triangles are isosceles, right?
okay.
So let's talk here, kids. I like this problem in a coordinate plane. And the nice thing about it in a coordinate plane is one of your sides horizontal, the top side. So if I want to talk perpendiculars to a horizontal, what kind of line is perpendicular to a horizontal? A vertical, right? So let's do this. Let's say, What's the distance from 0 up to 8 here, kids?
8.
So it's 8 units. So if I wanted to cut this in half perpendicularly, or that segment in half, what x value would I jump at and draw a vertical line at?
4.
Okay, so x equal 4. I'm going to do that. Draw a vertical line right here. Isn't this a perpendicular to that, perpendicular bisector to that side? Let me straighten it out here a bit.
Oh, yeah.
You got it, Kool-Aid man. Ooh, yeah. That's a perpendicular bisector, isn't it? Isn't this 90 degrees right here?
Do we have to have it out of
Oh, okay.
do we have to have it out of the triangle? Or can we just draw it in?
Hot dog, not like hot dog.
I have a question. I had a horizontal line. That was easy to get a perpendicular bisector in there. I also have a vertical line. Isn't that easy to get a perpendicular bisector in there?
Yeah.
Let's see. What's the height of my triangle?
6.
So if I wanted a horizontal perpendicular bisector on that left side, where would I draw my horizontal line at? At 3. Let's do that. Right here. Boom. Oh my God, that's pretty simple because immediately you know what happens here.
You know it's right there. It has to be.
Yeah, your circumcenter has to be right there. Oh, I want to fix that.
And it makes sense too.
Your circumcenter has to be where, kids?
4. Wait.
Okay.
What's b there or b square supposed to be like? Is square supposed to be like stupid or something?
I don't know. What point is this, kids, inside that triangle? 4 comma what? Okay, it means the distance then from here to, I don't know what my points were. This was D, this was E, and this was F. What this implies right here, if I call my circumcenter C, well, first of all, the circumcenter C is going to be at what point then? 4 comma 3, right? That implies to me this, kids. It implies that the distance from C to D is the same as the distance from C to E, which is the same as the distance from C to F. Check this out, kids. Let's just do C to D. What's the change in X from 8 to 4? 4. What's the change in X from 3 to 6? 3. Okay. What's the change in X from 4 to 0 from C to E? 4, and change of Y is what? What's the change here? And every time I do distance formula, I'd be plugging in 4 squared plus 3 squared. They're all the same. That point is the same distance. The distance from, all right, I say run a race. You're all standing at C. I say you can pick E, D, or C, E, D, or F to go to. Which one are you going to?
I'm not going to be running.
You can go to any.
Does it really matter?
No.
Is there an advantage to going to one over the other?
No.
Why not?
Well, the one
Because they're all like 4-3. What's the
Equidistant. Okay. Circumcenters are found by doing what to all sides?
Perpendicular.
Find a perpendicular bisectors. Where those lines intersect, that point of concurrency is the same distance to each vertice. You're not going to a side, but to a vertice. Now, let's compare that to what's known as, what's the word I just underlined up there?
Incenter.
An incenter is found not by doing perpendicular bisectors anymore, but rather by doing angle bisectors. This is an example for angle bisectors. It says in the figure shown at the right, NE is equal to what? N to E is equal to what? All right, so I'm going to write this down. N to E is equal to 6x plus what? Hey, stay with me, guys.
Okay.
N to E is equal to what? And then the other one is N F is equal to what?
4x plus
Now, if you look down here at angle C, kids, angle C, what's true about C to D? What is this in terms of my triangle or in terms of angle C? What does this red line do to angle C?
It's kind of a bisector.
It's kind of a, I'm going to say it's not kind of a bisector. I'm going to say it is a bisector, and the reason is because it cuts this bigger angle C into what? 2 congruent angles. Now, guys, we've talked about this, angle bisectors. If I pick a point right here, we say any point on an angle bisector is equidistant to either side of the angle. Now, when I talk about running to a side, I'm talking about a distance from a point to a line. And if I'm going from a point to a line, what angle do I have to assume on that path from my point to that line that we're trying to get to? A right angle. So if this is the point on the angle bisector N, the distance to this side right here has to be the same as the distance to this side right here, because we're going to run to that path or that finish line right here and form what angle? 90 degrees. So it says find the distance from N to what, kids? Find the distance from N to what?
D.
All right, we've got to find that first. I don't have a clue. I don't have a clue.
Aren't they gonna be the same as the other ones?
Ah, there it is.
Oh.
It's about,
6.
I don't know.
okay, how many centimeters is this then?
Well, x equals 7. That helps.
It's almost
Yeah, they all
one-
should be equal.
Yeah, they're all should be.
So you go N to D,
So you're saying this should be the same too?
8 centimeters away.
Yes.
It has to be the same because it's still on the angle
0.8 centimeters.
bisector, right? And any point on an angle bisector would be the same distance from that angle bisector to one side. Isn't that the same thing right here again?
Yeah.
Okay, so all three of these lengths are going to be what?
And
Same.
X equals 7.
So if I can find any of these sides, then we know all three sides. And I'm going to show you about an incenter here in a second. Watch this right here. To solve for ND, that's the same as these other two sides. So we're going to set 6x plus 1 equal to what?
4x plus 15.
Oh my gosh, it's like
Okay, and you said x was going to equal what here when I go through the math?
It equals 7.
it's 8.
X equals 7.
No, it isn't.
It's 8.
No, it's not.
This would be 2x when I subtract.
Yeah, that's what I thought. I can do quick.
7?
I was trying to do it. in my head,
Okay, so 6x plus 1, so it would be the same as 6 times 7 plus 1. What's that make one of those sides? So if I throw the 7 in here, after I solve this, x is 7. Yeah, each side's going to be how much? 42. So 42 is equal to that right there. Right? Oh, I'm sorry, 43. You want me to go 43, right? Yeah, you're right. So 6x plus 1, so 6 times 7 is 42 plus 1. That means all those distances are how much? 43 units, okay? Okay, I have a question here. You ready to listen to this one? Allie and I are going to run a race. Allie and I are going to start from basically the same point. I'm going to run straight to that wall and form a 90-degree angle. Allie's going to run over there to that corner from the same point. Who has the advantage before the race even starts?
You do.
Why?
Because you're faster.
Well, I don't know if I'm faster anymore. I might have been back in my front.
You have a longer stride, you know?
You're taller, so that
Because
means you have
she's
a
going
longer
diagonal, you're
So
going.
let's not even worry about how fast they can run. Does anybody have an advantage before the race
Your
even
power
Yeah,
is
you're
shorter.
perpendicular.
There's a shorter.
Okay, so the perpendicular distance is always the what?
Shorter.
Shortest. So, do we all agree that the distance up there for N to D is going to equal how much? 43. Can N to B, where's NB at? Find NB. Anybody got NB up there?
Top corner thing.
Okay, so it looks about
Guys, the distance from N to D, well, what kind of triangles formed there, by the way?
this is so hard.
Okay, this is a right triangle right here, isn't it? We know the distance from N to D is how much, kids? 43. So the question becomes this. If I look at N to B, which is right up here, and I'll put this in red, N to B right up here,
It's hard to set angle.
N to B.
guys, isn't this a right triangle still right here? Because that was a right angle down here.
Yes.
Isn't 43 like a leg of a right triangle? And isn't N to D like the hypotenuse of the triangle?
What's the height?
How is the hypotenuse related to a leg in any right triangle?
A squared plus B squared equals C squared.
I get the formula as a squared plus b squared equals c squared, but let's talk about it in comparisons of lengths.
Isn't
Longer.
it double?
It's always going to be longer, okay? So if the distance from N to D is 43, N to D was equal to 43, That is a leg or hypotenuse in this right triangle up here in red. No, the 43 is a what? It's a leg. N to B is equal to what? Well, it's a hypotenuse. Kids, can a hypotenuse be shorter than a leg? In other words, can that hypotenuse be 40 if this leg is already 43?
No.
No. So what's the answer to part B? No, it's not happening. Because the hypotenuse, which is N to B, cannot be shorter than a leg, which was the distance from N to D.
Gnarly, dude.
Okay. Now, this idea of incenter and circumcenter, I want to talk about this. I'm going to wait till you have that down here quickly.
You're smart.
You guys have that written down? Okay. I'm going to go back to this idea right here where the carny was at. Kids, we talked about that one point that was equidistant to all points on this, and we got a circle to go around it. When you talk about the word circumference, that means the distance, what? Around it. So circum means go around. Okay? Now, when we did angle bisectors, and we got a point on angle bisectors right here, because all these angles were bisected. These were bisected, this was bisected, this was bisected. They met here. Watch what happens here. It's pretty cool. Instead of a circle on the outside of all points, this circle is formed so it goes tangent to all three sides, like so. So an incenter is like, how do I pick a point inside of my triangle so that this point is the same distance, not to the corners, but to a side or a finish line, if you will. And we understand that running that race is on what kind of a path? It's straight. They're always going to be straight, but what angle am I going to form if I leave this incenter point to get to a finish line? Say if I'm going to the side BC, what angle am I going to form when I cross the line there? Well, it's a 90-degree angle. So that incenter is the point that's going to touch all three sides, and that distance is going to be the same to all three sides, forming what angle up here, kids? Okay, so let's use that idea. Let's use that idea on the last example here, and then we'll get you out of here for the day. Okay, last example. Solving a real-life problem. It says a school has what?
They have a fenced-in area in the shape of a scalene triangle to use
Scalenes?
Let me draw a scalene triangle.
Is that different side on all these?
Yes. Does that look like a scalene triangle to you guys?
Yeah.
Okay, there's my triangle. Draw a scalene triangle. I don't care what it looks like. Make it kind of similar, but make sure all three sides are different lengths. Okay?
Is that an obtuse triangle?
Yeah, scalene, obtuse. It's all right. Scalene, it can be obtuse, be acute. We just need to make sure that all three sides are what?
Different.
So if I measured all three sides. It says the school wants to place a swing set where it is the same distance from what?
All three fences.
All three fences. I have a question here, kids. Do you have a fence at a point, or do you have a fence on a side? How would you describe
On a
that?
side.
Fences make up sides, right?
Yes.
Okay, so if we're looking to say, I want to put a swing set so it's the same distance from all three fences, we're talking about finding a distance from a point
To a side.
to a side. So we're looking from a point to a perpendicular path to each side. So it said, should the swing set be placed at the circumcenter or the what? Incenter of the triangular playground. What would you say?
In-center.
I want it to be the in-center because the in-center is the same distance to each side. The circumcenter is the same distance to each corner, if you will. Okay? So,
But also, wouldn't they be pretty similar?
it is. I mean, I don't know where it would be, but
A square playground.
might be right about here.
That is a weird
The
thing.
point might be right about here to say, distance perpendicularly. Yeah, this is kind of a tough one here to find that point.
Yeah, how do we?
Let me just can I kind of guess?
Oh, you have to use that.
Angle bisector, so maybe right about here. So if I draw a perpendicular to this line, a perpendicular to this line, and a perpendicular to this line, aren't these all three about the same? Okay? It's not going to corners, but it's going to what? Sides. And when it goes from a point to the sides and it's the same distance, and these distances are the same, you would be looking for an in-center. Because you're going from point, you want the distance from your point to the sides to be equal. All right, kids, there's so much going on here, and there's a lot of good stuff in here. I get geeked up about this stuff. I think it's so cool. Okay. What I'm going to tell you is this. I sent out a new online page, so I'm going to encourage you to take a look at that. It's actually not due until next year, but
Whoa.
It's funny because it's at the end of the school year for 18.
Yeah, that's crazy. It's gonna be 29.
January 4th will be the due date.
Lunch announcement.
Okay?
Reminder that for a la carte today, drinks only. Also, the lunchtime today will start from the opposite end where normally a la carte starts. So when you come in, you're going to start lunchtime at the opposite end as we usually do.